Is and we're still in 1.1. This is the second half of 1.1 on functions, and there's a few more things that we need to talk about. And one is a special kind of function. It's called a piecewise function. And so a piecewise function is a function that's defined by two or more equations over a specified domain. So let me give you an example of a piecewise function. So I have h of x is equal to, and then we have this bracket here, x plus 2 for x greater than or equal to 2 and x minus 1 for x less than 2. Now these particular functions have very interesting graphs, but we're not going to talk about their graphs today because we are going to talk about graphing in 1.2. So we will talk about the graphs of these later, but for right now we just want to use our functional notation and understand what this means. So this particular function is defined basically two different ways. So for all x values greater than 2, this is the way my function behaves. For x less than 2, so anything smaller than 2, 0, 1, negative 2, then my function is going to behave like x minus 1. So if I want to evaluate it, remember my functional notation here, h of negative 1 means I'm going to take negative 1 and plug it in for x in the function h. H is the name of our function. So where is my function defined for negative 1? I don't just come up here and put it into both because my function isn't defined. I'm looking for the part where it is defined at negative 1. And so negative 1 is smaller than negative 2. So this is the piece that I'm going to plug in my negative 1 into. So h of negative 1 is negative 1 minus 1, which is negative 2. So we can say that h of negative 1 is negative 2. All right, so let's look at another value. Let's say h of 4 is equal to, all right, so now I'm looking for where is 4 defined. Okay, so 4 is larger than 2, so that means I'm going to plug in my 4 into this top piece for my value. So I end up with 4 plus 2, which is 6. So that means h of 4 is equal to 6, right? These would be ordered pairs also when I go to graph them of negative 1, negative 2, and 4, 6, right? This is my x value. My h of 4 is equal to 6. This is my y value. All right, so let's do one more of those. How about h of 2? All right, so we might need to think about this one a little bit more carefully because here 2 is actually where my functions change. So I'm looking for the place where h is defined actually at 2, and that would be in this piece here because this has said x is greater than or equal to 2. We haven't talked a lot about inequalities yet, but the extra line underneath means that it's equal to 2 as well. This one is x is strictly greater than 2, so that means everything just a little tiny bit smaller than 2, but not actually 2. So when I evaluate h of 2, since this is where 2 is defined, I'm going to plug it in here. 2 plus 2 is equal to 4. That means h of 2 is 4. All right. Let's work on one more example. So let's do one that's a little bit. So this time we're going to have 3 functions, or it's going to be defined in 3 different pieces. That's why we call it piecewise. So for the square root of x, we're going to say that that's for all x's greater than 0. For 3 plus x, this is where my function is defined between negative 2 and for x is less than or equal to 0. And my x squared for all x's less than or equal to negative 2. Okay, so there's no overlap. So my domain is broken into specific parts, right? So there's no overlap. So there is a 0 here and a 0 here, but the 0 is only included here. And there's a negative 2 here and here, but the negative 2 is only included down here because of the equal sign as well. So let's evaluate some points here. So let's look at f of 4. So the hardest part here is just making sure that we're putting in the right place. So 4 falls into, right, greater than 0. 4 is bigger than 0. So I'm going to plug in my 4 into this piece. gives me 2. All right? So let's look at f of negative 1. F of negative 1, that falls between 0 and negative 2, so that means I'm going to plug my negative 1 into this piece here. So I have 3 plus negative 1, which is 2 again. Right, so let's try f of negative 5. So negative 5 falls into my x less than or equal to negative 2. It's smaller than negative 2. And I plug that into my x squared. This is this piece, so I have negative 5 quantity squared, which gives me 25. Right, so let's look at the changeovers as well. So let's look specifically at f of 0. So this is where I need to make sure that I'm plugging it into the right place. This is for strictly greater than 0. This is the piece that includes 0 because of this extra equal to sign underneath here. This is read x is less than or equal to 0. So 0 is included in this one. So f of 0 would be 3 plus 0, which gives me the 3. And then the last one, f of negative 2. So negative 2, I want to be careful about where I'm putting it in. Up here, it's defined at 0, but not at negative 2. It's strictly greater than negative 2 here. So here it's x is less than or equal to negative 2, so the negative 2 is included in this one, and so I plug it in here. So I have negative 2 quantity squared, which is 4. Actually, I put that in the wrong place. There we go. It's 4. So negative 2 quantity squared is equal to 4. All right. So we will talk later about the graphs of these. They're actually quite interesting, but for right now, we're just evaluating at piecewise functions. Okay. So the next topic that we're going to talk about in this is I want to do just a couple of these. I want to talk about solving. This is kind of a notation issue that I just want to talk about. So f of x equals 0. So we're going to see this a lot later on. We're going to talk more in detail with this when we get into the next couple of sections. But for right now, I just want to make sure that we're on the same page with understanding. So I want to remind us that y equals f of x. Okay, so really y and f of x are interchangeable. And so when we're solving something, if I'm said find f of x is equal to 0, then that means I'm actually going to plug in 0 for y because y equals f of x. Okay, so let's do an example of that. So let's say I have f of x equals 3x minus 8, and I want to find where f of x equals 0. So that means I'm going to, a lot of times when we're solving equations, what we do is we replace f of x with y. So I have y equals 3x minus 8, and this f of x equals 0 is interchangeable with y equals 0 because y equals f of x. Okay, I'm going to plug in 0, and now this is just a simple equation that I solve. So I add 8 to both sides. I have 8 equals 3x, and so my x equals 8/3. So the way that I would write that back in my functional notation would be f of 8/3 is equal to 0. Or, right, this is an alternative, but in this case, since we started out with this, we'll put it back in this. Okay, let's do one more different type. So let's look at the quadratic. This time I'll call it g, because everything can't always be called f. So I have x squared plus x minus 20, and I want to know where g of x is equal to 0. I'm remembering that y equals g of x, right? It doesn't matter what the name of the function is when I use this notation, y is equal to that notation. So I want to know where y is equal to 0. So let's replace y. Now I'm writing very carefully every step. It's okay once you get comfortable to just plug in y equals 0. That's perfectly acceptable. My next step is 0 equals x squared plus x minus 20. This is a quadratic now that looks like I can factor it. So let's do that. If you don't remember how to solve quadratics, go back and watch. There's 4 different ways that you can solve them. This is the factoring method. So I know I'm going to have x and x here to get the x squared. I need the 20 in the back, so this sign is minus, so that means I'm going to have one sign that's positive and one sign that's negative. I know that 5 times 4 is 20, and 5 minus 4 is 1. So I need to put in positive 5 and negative 4. So now my last step is just setting equal to the individual factors equal to 0. I have x plus 5 is 0, which gives me an answer of x equals negative 5. X minus 4 is 0. So this one I get two different solutions, so I can write them both like this. F of negative 5 is equal to 0, and f of 4 is equal to 0. All right, so that's solving f of x equals 0. A couple examples. The last thing that I want to talk about is finding the domain of a function. Okay? And so when we're finding the domain of a function, so the domain, again, let's just do a quick reminder. The domain of a function are all the values of x that are where my function is actually defined. It's basically, the short answer is all the x's that I'm allowed to plug in, okay, that don't make my function undefined. And so there's two ways that domain can be explained. Okay, so first of all, it can be described explicitly. Maybe you have f of x equals x squared and they only want you to use x greater than or equal to 0. This is an example of the domain being explicitly defined. It's basically set out. Somebody wrote down the function and said, you can only use these x values. Okay? Now, a lot of times what we find is they're implied. And so when they're implied, then we kind of have to know what real numbers that we can use for which our expression is defined. Okay? And so one of the ways that we can, so there's some things that we're looking for that cause domain restrictions. So the first thing is sometimes we have a word problem. And basically this is a contextual issue. So let's say that my function, f of x, was describing some process where it was trying to predict the cost of producing a certain number of boxes, where x was the number of boxes. So we have some function here, and f is stated here, and it's stated somewhere in the words that x is the number of boxes that are produced. Okay, when you think about a manufacturing company producing boxes, it only makes sense that the boxes there would be a positive number of boxes, right? I've never heard of anybody talk about, well, I'm going to go make -3 boxes. Okay, so this is a contextual issue based upon the context of the problem. Right, so the ones that we're going to run into a little bit more often are when we have things, we know that there's certain things that we're not allowed to do in math, and we've discussed them before, and one of them is to take the square root of a negative number. Okay, so this is an undefined situation. We'll make that a specific number because if a is negative, it actually does work. So the square root of -3 is undefined, and so this is the type of thing that we're looking for, is for things that we're not allowed to do. So whenever I see something with a square root in it, or any sort of root, I always want to look at it really closely. We'll explain how we're going to do this more specifically. And then another situation that we've talked about already in here is division by 0 is another undefined. So taking the square root of a negative number is one possible thing that will give us a domain restriction. The other one is division by 0. So whenever there's a possibility that these two things could happen, I need to look very closely at them. Okay, so let's look at f of x equals the square root of x plus 4. So I have a square root. That immediately tells me I need to be thinking to myself, I know that I'm not allowed to take the square root of any negative number. The square root of 0 does in fact exist, right? You can take the square root of a negative number. So the smallest number that I could put in here, if I used x equals -4, that gives me the square root of 0. And that is a thing, if the square root of 0 is in fact 0. And so I need a way to figure out how I can write my domain, right? If I plug in something like -8, I can see right away that -8 plus 4 is going to give me -4. So how do I figure this out? So, and this applies to any even root, not to an odd root like the cube root, but the square root and the fourth root, they all have to be positive, the numbers that we put into them in the real number system. So we take this out and we set it greater than or equal to 0, because again, I said -4 is possible, right? I can plug in -4 because -4 plus 4 is 0. And then I just solve this. So x is greater than or equal to -4. I just solve this inequality just like it's an equal sign. The only time I have to worry about anything other than that is if I'm dividing or multiplying by a negative number, and then in that case I have to flip the sign. So this gives me a domain restriction of x is greater than or equal to -4. That's my domain restriction. So I'm allowed to use any number to put in here as long as it's greater than or equal to -4. So anytime I see an even root, I pluck what's underneath the radical out and I set it equal to greater than or equal to 0. I solve that. That's my domain restriction. All right, so let's look at a possible division by 0. So I have f of x equals x plus 1 in the 1 over x plus 1. So if I just had 2 in the denominator and my x was in the numerator, I wouldn't have to worry about my domain restriction, because if I just have a number down there, that can't equal 0, it's just a number. But if I have a variable in the denominator that could possibly make my whole denominator equal to 0, then I need to throw that point out. Okay, so I'm allowed to use anything else, right? If I use 3, then I get 1 over 3 plus 1, which is 4. So I get 1/4 here. So I'm allowed to use all the other numbers. It's just that if x plus 1 is equal to 0, that's when my problem falls apart, because that's when I'm dividing by 0. So I find out here that x equals -1 by solving for x. That means here that my domain basically is all real numbers except x equals -1. Or I could say x cannot equal -1. Right? Those are both my domain restrictions. It's okay for me to use anything else. Right? I can use a negative number. If x is -2, then I would get 1 over -2 plus 1 would just end up giving me -1, because -2 plus 1 would be -1, and 1 divided by -1 is -1. So everything except for that -1 I'm allowed to plug in. So these are our two main ones, when I have an x in the denominator and when I have an x in the radical. Now, this is assuming that I have basically my equation solved either for f of x, right, or y is interchangeable. So I want to probably do that first, because then it's easiest to see what my domain restrictions are. Once I have f of x notation, then if I have a square root, I approach it like this. If I have an x in the denominator, I approach it like this. All right, so let's make things a little bit more interesting. Let's do a little bit of a combination here. So what if I have f of x equals 1 over the square root of x minus 1? So I have a little bit of both, right? So I have both this square root problem, and I have a variable in the denominator in my problem. Okay, so I need to approach this one with a little bit more care. So first of all, when I'm doing a square root, right, I see the square root, I immediately know that x minus 1 has to be greater than or equal to 0. If that would be true, if f of x was just x minus 1, x would be greater than or equal to 1, and I would be good to go. This is my domain. Okay? However, now I have the square root of x minus 1 in the denominator. And in my denominator, I know I'm not allowed to divide by 0, right? So this one goes with this here. So what I need to do over here is a very similar. I know that this has to be greater than, my square root has to be greater than or equal to 0, but because I'm in the denominator, it means that I could strictly have to be greater than 0. Because it's in the denominator, I know I'm not allowed to divide by 0. So I have x is strictly greater than 1 here. So a little bit different, where this one I'm allowed to plug in 1, this one I'm not, right? I can use everything just a little bit bigger than 1, but not 1. So my domain restriction on this one is x is strictly greater than 1. If I just had the square root of x minus 1, it would be greater than or equal to 1. All right, So let me do one more interesting example. What if I have x minus 2 in the denominator and x is x plus 3. Okay, so what I can do here is I have two different things here, okay? So again, I have in the denominator the square root of x plus 3. I know that for a square root, I know I need x plus 3 is greater than or equal to 0, but again, it's in the denominator, so I can say it's strictly greater than 0. So now I have x plus 3 is greater than 0, and I have x is greater than negative 3 is my answer. And this is my domain restriction here. If I'm given any other function, for instance, I have x squared plus 4x minus 6, or f of x equals 3x minus 2, I look at these and I can see that I don't have a square root, right? No even root, and I don't have any division by any variables. And so for these, I can immediately say that my domain is all real numbers. This is just a symbol for all real numbers. Okay? So once I have it, if I have f of x notation and I have f of x is equal to something or y is equal to something, I can immediately say that if there isn't a square root or there isn't a division by a variable, then I can see that it's all real numbers unless someone explicitly states underneath it that I can only use these x values. All right, so let's just do one that's words. So let's look at the volume of a sphere. Okay, and the volume of a sphere is 4/3 pi r cubed. All right, so this time my r is my variable. So since I'm talking about the volume of a sphere and my r is my radius, then as my r has to be greater than 0 or else I don't have an actual sphere, right? And I've never seen a sphere with a radius that's negative. So this is kind of one of the implied ones where if I just looked at this and I had no idea what it was, I would say, oh, there's no domain restriction because there's no square root, there's no divisible division by the variable, but it is the volume of a sphere, and I can only have a sphere if I have a positive radius. So in this case, my r would be greater than 0 is my implied domain in this case. All right, I hope that clears up any domain issues, and we will talk about 1.2 next time.